everybody. I sat through the earlier sessions, and there was a lot of very consistently good advice about platform engineering, and I was checking notes and see if my implementation live up to the standard. I think I'm okay. But here is, I'm going to talk to you about a type of platform, and maybe not the most common kind you run into, but this is sort of like a case study of how we tried to solve a problem but ended up accidentally almost doing platform engineering. So this is about my tenure at Twitter. I was at Twitter for almost 12 years. It is mostly the second half of it. Now I'm no longer at Twitter for reasons that hopefully is well known. But let's get to the topic. So I want to start with a story. So when I was 9, I grew up in China, so I read about the story in Chinese. So there's this wizard of an electrical engineer and scientist, right, Charles Steinmetz. So he was originally German. He came to the US. He became sort of a wizard figure in this local town. And one of the most famous anecdote about him was he was asked by Henry Ford to debug a problem about the generator. Right? So he's like, I don't need tools, give me some pen and paper. And he would just sit there and thought. Right? So on the second night, he asked for a ladder, and he climbed up to the generator. Apparently that's kind of tall, or maybe he was short, and then marked on the side and say, replace the plate here and also 16 rounds of coil. So the rest of the engineers did as he said, and they did, and the generator performed to perfection. So later, he sent a bill to Ford, say, asking for $10,000. I looked it up. $10,000 back then is about $200,000 in today's purchase power. So for 2 days worth of work, that's not so bad. Right? And Ford was a little bit taken aback, said, why are you asking for so much money? He said, this is his explanation. Making the chalk mark, $1. Knowing where to make the chalk mark, the rest of it. Right? So ever since then, whenever I see performance engineering stories, usually on Hacker News, it's usually how it goes. Like, here is a core loop, and we changed that one line in this loop, and suddenly our performance went up by 300%, right? And then it inevitably goes to the front page. Everybody has a great discussion about what is, this strange AVX vectorized instruction, or how you fit things into L1, L2 cache. Everybody is like, oh, if only I knew, right, like where to find those one-line changes, I can be Hacker News famous, and I can make a lot of impact. So that tends to be the popular conception of what performance engineering is you know exactly where to look, you make that magical touch, and then things automatically get better. But is that true, right? Is that sort of, should we hire basically a room of wizards and then set them loose and then go around and holding a chalk and then marking all over the place, right? So hold that question for a sec, and I'll answer that in 5 minutes. So a little bit more about who I am. So I was actually at QCon, speaking at QCon SF in 2016. Back then I was talking about caching. Right? I spent my first half at Twitter mostly managing caches and developer caches. I weathered through a dozen of user-facing incidents, and I so spent lots of time digging in the trenches. And actually, shortly after giving the talk, I founded the performance team called IOP. You can ask me what IOP stands for after the fact. I'm gonna give you at least 3 answers. So I started the performance team at Twitter in 2017. And that went on until last year. So generally, I like things about systems, especially distributed systems. I like things about software and hardware integration, and then performance really is an area that allows me to play with all of them. So that is what I have spent time working on. So today, I want to talk to you a little bit about performance engineering. So this is the year. If you want to start pivoting into performance engineering, this is the year to do it. So how many companies here have given some kind of cost effectiveness or efficiency mandate? Right, so there's one reason. This is one reason to care about performance. Right, so if that's on your mind, here's what you can do. So number one, I want to first start by saying a little bit about why we actually need performance engineering now more so than ever. So there was this wonderful talk by Emery Berger, who is a professor at University of Massachusetts. And in his talk called Performance Matters, he pointed out a fact. He said performance engineering used to be easy, right? Because computers get faster about every 18 months. So if you're a performance engineer, you just sit on the beach, drink your cocktail, and buy the next batch of machines in 18 months. And I'm like, that's wrong. If it's that easy, then you don't need it, right? Like, in fact, what happens is people don't really hire performance engineers until they are extremely large companies, and the rest of the engineering department just sat on the beach, drank their cocktail, and wait 18 months and then buy the next generation of computers, right? So now the moment has finally come that you actually have to put in work. And why is that? Well, this is a slide about all kinds of hardware features. So it's intentionally made busy, starting from things like NUMA nodes and PCIe accelerators like GPUs and other devices which have been on the market for at least 15 years. And there's all these terms that represent certain kind of specialized technologies that you may or may not have heard of, right? There's CXL, there's vectorization, programming NICs, RDMA, whatever. The point is, there's a lot going on in hardware engineering because we have all these sort of petty laws of physics getting in the way. So there's the power cap, there's the thermal cap. You cannot make a computer just run faster. Right? Simple things run faster, that's the best. But instead, you do all these tricks. So the heterogeneous evolution of the hardware means it's getting really, really difficult to write good program or the right kind of program to actually take advantage of them. So if you think programming many core computer is difficult, just wait until you have to learn 20 different new technologies to write a simple program. Right? So it's really getting out of control. On the other hand, our software engineers are not doing ourselves any favors, right? If you look at a modern application, it's highly complex. On the left, it's a joke by XKCD, but it's very much true. You have this impossibly tall stack, and nobody knows what your dependency tree really is, and nobody really wants to know. And if you zoom out and you say, let me look at my production, well, your production is not even one of those tall stacks. Your production is a bunch of those tall stacks, right? And no matter how complex a graph you draw to represent the relationships between the services, reality is usually much worse. So on the bottom right is a graph that is actually quite old by now. That's a 5-year-old graph back from when Twitter was simpler. And this is the call graph between all services, right? And you can see the number of edges and how they connect with each other. It's enormous headache. So the problem here is that things are complex. So if Steinmetz were to live today and were to solve what is the software equivalent of a generator, I think what he's going to be facing is you have these 6 feet tall generator packed into, I don't know, like a 40-foot long, right, corridor, and then you have an entire warehouse of them, and that's not the end of it. You have 3 such warehouses connecting to each other, and to generate any electricity at all, you have to power up all 3 rooms, and they constantly are bustling. So when you have that level of complexity, basically there is no room for magic, because who needs magic when you have systems of complexity instead? Right, so the answer is no. We cannot purely do performance engineering relying on knowing everything and being able to hold the state in our head, because reality is far more challenging than that. So the answer basically is treating complexity with the tools that is designed to handle complexity. And the language for complexity, one of the languages for complexity actually is systems. And this is something that has been mentioned over and over again in the talks below. But I think systems it's not sort of mythical, right? Systems is essentially you have a large, you have a lot of things, and those things are connected. And system essentially is building a model to describe the relationship between different parts. And if you see the fundamental reality through that lens, then what is performance? Performance is merely a counting exercise on top of such relationship, right? You're counting how many CPUs or how much memory bandwidth or how many disks you have. And you're counting how often are they used and to what extent are they used. But the key here is you need to have the system model in place, so you have the basic structure. We need to count these resources at the right granularity. If you care about request latency, for example, and the request latency tend to happen on the level of milliseconds, then you need to count at those time granularities. Otherwise, the utilization would not reflect what the request is experiencing, right? So, and all of these things will change over time, and therefore this exercise will have to go on continuously. So performance as a system property allows us to draw some parallels with other system level properties. I think those are also fairly well understood. For example, there's security. Security, the intuitive way of thinking about security is that the weakest link determines the overall system security, right? So it's sort of like a and relationship. So anything that fails means the whole system fails. Availability, on the other hand, is much more forgiving. So if any part of that system works, the system is available, right? And performance is somewhere in the middle. So performance loosely can be seen as the sum of all parts. So you add up the cost of your parts, or you add up the latency of all your steps, and this means that when we approach performance, we often can trade off. We can say a dollar saved is a dollar saved. It doesn't matter if it's here or there, because in the end, they all add up together. And performance also links to some of other higher properties, or maybe business level concepts that we care about, right? So businesses generally care about reliability. They want their service to be available. And performance is a multiplier of that, right? Better performance means you can handle more with the same resources. And cost, on the other hand, is inversely related to performance. If you have worse performance, if your performance is lower, then you have to spend more money to get the same kind of availability. So through these links, this is how performance ties itself to actually the overall business objective. So the other thing about performance engineering implies that things can be made better. In particular, performance can be made better. So can we make that claim? And I really like this book that's called Understanding Software Dynamics. In the first chapter, what it establishes is that there is a limit. So there is a baseline saying how slow should it be. For example, you can never violate the law of physics. You cannot run faster than what the CPU can run according to the clock, right? If there's a delay because of PCIe, it cannot transfer data any faster than the physical limitation of those links. So all of these boundaries and all of these constraints actually tells us if you do everything right, what can you expect? Right, so the other aspect is predictability. If you keep measuring things over and over again, over time you get a distribution. Right? So you can see how bad are things at the tail, how bad are things in the worst cases. And those tend to have an effect when you have a very large infrastructure. And on the other hand, you can understand the consistency, and this means if you measure them over time, this is the kind of behavior you can sort of characterize and aggregate. So the TLDR is this: good performance. So if you design something really well for performance, I think good performance engineers or good software engineers tend to converge on the thing, maybe a same design that tends to look similar, right? So if you know what good performance looks like, what you can do is you can measure what you actually get. If what you actually get is different from what is good, that delta is the room for optimization. So because such a limit exists, and because we know how to measure them, we can do optimization. Another thing I want to mention is just there is a structure in performance engineering. So just like building a house, the most important thing is you have the structure right? After that, you want to do the plumbing, because once you put the drywall on, you cannot go back and change the plumbing very easily. There's an analogy here. If you want to design a program, how you communicate between different threads, between different parts of your program is really important, because those are hard to change. The kind of ideas we associate with performance engineering in anecdotes, like changing an inner loop, those are actually the least important, because those are the easiest to change. You can always change one line of code very, very quickly, right? But you cannot change the structure of a problem. So when you do performance engineering, focus on the things that cannot be changed very easily or quickly, and then eventually you get to those local optimizations. All right, so now we say we know how to do performance engineering just in concept. But the talk is about how to do performance engineering at Twitter scale. So how do we do it at scale? Well, we just basically follow the blueprint, which is we want to build a model for the system. We want to do counting on that system, right? But what actually happens when we build that model and when we do the counting at scale is we translate what is otherwise like sort of reliability or system admin or magical wizardry engineer looking into an isolated piece of code. If you want to do it at scale, it actually gets translated into a data engineering problem. So let's use this as an example. If you think about modern software as a local runtime, and software engineers are very good at abstraction, right? So we have all these layers. We have our application code, which sits on top of a bunch of libraries. It may have a runtime like the JVM. And then we have the operating system, and underneath it, we have the hardware and then even the network. Right? So all these layers of abstraction actually provides the structure of how we would think about software in terms of hierarchy. And once we have this mental model in mind, we can collect these metrics, because in the end, what we care about is how resources are used, right? So you can count these things. At the bottom, you have your hardware resources, but they get packaged into all these kernel-level syscalls and other low-level functionalities, and then you can count them to get a sort of a higher-level unit that you can do tally on, and so on and so forth, until you get all the way to the top of the application. So what we did is we essentially said these are the data we need, and these are the data that would apply universally. So generally, so now we're in the domain of sort of essentially data engineering. And in data engineering, what you care about are two things. One is where you get the data and what data you're getting. Number two is what are you doing with that data, right? How are you treating them? So that's exactly what we did. So when it comes to data generation or signal generation, well, one thing we realize is, remember, performance is about counting resources at the right granularity. One thing that is unique about performance is that actually the granularity that performance looks at is actually much finer, generally speaking, with general observability, right? If you get metrics once every minute or once every 10 seconds, that's considered fairly okay as an interval. But a lot of the things about performance happens on the level of microseconds or milliseconds. So often you need to collect signals at those levels. So if you have a spike that lasts only 50 milliseconds, you'll be able to see it. And so that requires us to write our own actually sampler or systems of samplers that gives us all the low-level telemetries at very high frequency at very low overhead. And the way to get there is we actually wrote our own. We heavily used the eBPF. If you have not heard of it, look it up. eBPF, which gives us low overhead and also lets us looking into the guts of the layers of abstraction and pretty much get any visibility we want. And we also have a project called long-term metrics, which is synthesizing pretty much all levels of metrics. So you can correspond response latency with very low-level resource utilization. So you can see, is this request slowdown due to a spike in CPU usage or something else? Right. So because we are a performance team, we're not explicitly a platform team. We actually, so the point of building all this data infrastructure is to solve real problems. So one of the ways we use our data is that we look at everybody's GC, and then we concluded what is the right distribution of GC intervals and how often they should be running. And then we just generated a set of instructions and UI to tell people how to tune their GC automatically, right? So it would compute it for everybody, and you would see the result. And we also have fleet health reports and then showing how much bad hosts is actually becoming outliers and slowing everything down. We also have like all these utilization reports and telling people where their utilization is and where they should be and how much they have room to improve. So one of the unintended usage actually is people started using our data set for things that may or may not have to do with performance engineering, right? So capacity engineers decide they want to validate their numbers using the data we have. And service owners see what we do when it comes to optimizing for certain services, and they're like, we know how to do this. It's a simple query, we can copy yours. And they started doing it on their own and actually saved quite a bit in some cases. And just because we have data in queryable, like SQL-ready state, several teams actually start to prefer the data set we produce because they're just easier to use. So that is localized data engineering for performance. So I took a bit of we took a bit of shortcut here, as you can see. We actually did not really understand how the mapping between these layers together, and that's because Twitter applications actually tend to be very homogeneous. We have all these, we have libraries like Finagle and Finatra, which allows us to cut corners because all applications actually look alike. So if you want to understand a heterogeneous set of services, you may need to do things like tracing and profiling, so the relationship between different layers might be more obvious. So, but then we say we zoom out, right? Like we have all these local instances of like applications, but they don't tell the end-to-end story. When you have a very complex application that has, that has relationships between services, we also need to understand how they talk to each other. And this is often in the domain of tracing or just distributed system understanding. And here we take the same approach. We say, what is the system here? The system here is you have all these services and they talk to each other, right? So when they call each other, that's when they are connected. So we capture these edges, and then same thing, we do counting on top of that. Counting is, here come in very different flavors. You can do counting with time, right? You can say how much time does it spend on this edge. You can do counting on resources, like how many bytes, or what kind of attributes is propagated. Anything you can think of actually can be applied to the edge. But the most important thing is the structure, which is this tree-like graph where all the interactions are happening on top of. So we did very similar data treatment. So first we say, let's improve the signal we're gathering. So Twitter was actually Twitter started the Zipkin project, which later became the standard in open telemetry. So all of Twitter's services actually came with tracing. But tracing data is particularly fraught with all kinds of data problems. Some of them are inevitable, like clock drift. Some of them are just due to the nature that everybody can do whatever they want, and you end up having these issues like missing a field or having some kind of garbage data in the field. All of those actually requires careful validation and data quality engineering to iron out. So this took numerous attempts to get to a state where we can trust. But on top of that, we then can build a very powerful trace aggregation pipeline. What it does is it collects all the traces instead of looking them one by one, because nobody can ever enumerate them, right? You started putting them together and building indices. And indices really is the superpower when it comes to databases. We have indices of traces themselves. We have indices of the edges. We have indices of the mapping between the trace to the edges. And all of these data are queryable by SQL. And what we were able to do are things like, how do services depend on each other, right? So this is a screenshot of what we call a service dependency explorer. It tells you who calls who to execute a particular high level, like if you were visiting Twitter home timeline, how many services are called along the way, and for each call of the highest level, how many downstream calls are necessary, right? So you instantly get an idea of both the connectivity and also the load amplification between services. We also did a model which is turning into a paper called latency. Essentially allows you to do causal reasoning of who is responsible for the latency that you're seeing at the high level. So the latency propagation or latency critical path is a product. What this allows you to do is say, you can ask what ifs. What if I migrate this service to a different data center? What if I make it 10% faster? Does it make a difference overall? Right, so all these properties can be studied. And we did lots of analysis on demand because aggregate tracing often can answer questions that no other data set can give you answers for. So one unintended usage of this data set is the data privacy team realizes that they want to know what sensitive information is in the system and who has access to them, right? And they realize the only missing thing they have is they don't have the system. They don't have how services connect to each other. And this data set that we built, mostly to understand how performance essentially propagates through the system, ends up being the perfect common ground, right? They throw away all our accounting. They replace that with the property they care about, but essentially they kept the structure of the system in place, and this allows them to do their performance and privacy engineering with very little upfront effort. So, in summary, basically we spend majority of our time doing data engineering, which is certainly something I was not thinking about when I started, but it made our actual work much easier. So we were the #1 and primary dog fooding, customer of our own platform, and we were able to do all of these. So each thing I list here on the top probably is on the order of, tens of millions, no big deal. But we were able to finish each task in a few months, right? And all of that was possible because we were using the data that we carefully curated. So any question we have is no more than a few queries away. So this essentially is the power of platform engineering. So toward the end, actually, we started building even more platforms, right? As I said, we cheated on the sort of software runtime as a system because we sort of just read the source code and understood what's going on, but that's not the sustainable way of doing it. So we actually very much intended to do program tracing, program profiling, and get the data there treated very much the same way as we were treating other data, and turn that into a data set that anybody can look into. And also we were thinking about having a performance testing platform, so whatever change you want, you can push through the system and it will tell you immediately what the difference this is with any of the other settings you care about. But a lot of these things did not happen because we all get kicked out of Twitter. So, that was the technical side of things. I want to, to fit in this track, you have to talk about things that are not just technical, right? Like, how do performance engineers fit into the broader organization if this is the sort of thing we do? The short answer is we don't fit in. So, I think the best analogy might be I'm not sure if you've watched Finding Nemo 2. There's this octopus that is escaping from the aquarium. I sometimes think of the performance engineering team as the octopus because we are dealing with system property here, right? Like whatever we do can take us really to any part of the system and maybe talking to any team in any part of the organization. So whenever executives or management tries to box performance engineering into a particular part of the organization, which is very hierarchical, we somehow will find something to grab onto and then sling ourselves out of the box that they drew for us. So if you are interested in performance engineering or really any of the system properties like reliability, security, and you care about having a global impact, actually you have to deploy a lot of thoughts into managing the hierarchical org, which is, I think, fundamentally incompatible with the way these properties work. Right? So you have to take some first principled approach, figuring out the fundamentals, and then be very clever about it. So I think the fundamentals are actually very straightforward. Right? Like performance engineering, you either line up with the top line, which is making more money, or you line up with the bottom line, which is spending less money. Right? Sometimes you need to pick which one is more valuable. Sometimes you will switch between them, but you need to know what you are dealing with. Like the value has to be associated with one of these. And it will affect questions like who is your customer and then who is your champion, because you need to know who you're helping. And also the decision-making structure is really important. If you have a top-down instruction, structure of decision making, you find the highest attach point you can find, and that person is going to give all the commands on your behalf, and then your life is easy. If you have a bottom-up, organization, then you need to sort of grow a fan base, essentially, people who like using your thing, and they will advocate for you on your behalf, right? So constantly think about like how to align incentives, how to convince others to do your bidding. And one last thing, how to get promoted and recognized, because that's not obvious. If you're doing this type of work, you are not the same as majority of the rest of the engineering org. So your story has to be straight. And I have some other thoughts. So one thing early on that was a little controversial was that people said, if you have a performance engineering team, does that mean people won't do performance work elsewhere? Are you going to do all the performance work? I think the answer is absolutely no. So in any engineering org, there will be lots of often very good engineers who are willing and capable of doing excellent performance engineering work. And the idea is but they won't join your team, right, for various reasons. I think the answer is always you let them, right? Not only do you let them, you help them. I think the point of having performance engineering is the symbolic significance of having a performance engineering team cannot be underestimated, because it means the org value this type of work. So, and also nobody ever shoots a messenger who delivers the news of victory. You can just take out your bullhorn and give everybody credit. You will still come out as a hero, right? Like so I think be a focal point where people can come to you in the right context, say let's talk about performance, and they contribute their ideas. They even do the work for you, and then you give them credit. You make them look good. I think this is a great way of having a culture in the end that values this kind of a collaborative approach, and also values just this type of system thinking and global optimization in general. So there's also a bit of a funny boom and bust cycle going on with performance engineering, which is the opposite of the general business. When the business is good, everything is growing, nobody cares about cost because you're just floating in money. Nobody cares about performance, and that's okay. Nobody gets fired when the company is doing amazing, right? But the reverse could be true. The company is really doing poorly. Like everybody is so stressed out. At this point, you can be the hero. You can say, I know how to make us grow again. I know how to make us grow again. I know how to save money. And then now everybody wants to work with you. I would say take advantage of reverse, boom and bust cycle. Do your long-term investment when nobody is paying attention to you, but have all the plans ready when the company is in need, when the business is in need, and you can be there ready to make an impact felt throughout the company. So I presented sort of the things we did and how we fit in, and it's all nice and neat. I figured this out, but as everybody could probably guess, the birth of anything was never this neat. It's very messy. So this is what actually happened. What actually happened is I had no idea back in 2017 like any of this would happen or how I would go about it. All I had was a niche, right? So I just had my first baby. I was like sleep deprived constantly and holding a baby in my hand like 16 hours every day. And I was in this sort of dazed moment. I started thinking about performance. So I wish I was in a hammock, but that was never true. But I had this sort of drifting into this thoughts, like just think about performance in a very deep philosophical way. If you don't believe this is philosophical, just replace performance with happiness and you'll see my point. Right, so I spent months with it, and then finally a vision occurred. I figured out the ideal performance engineer who knows hardware, good at software, has operations experience and can do analytics and can speak business and also deal with any kind of people you would run up and down the org. So, might as well walk on water at that point, right? So a unicorn, not just any unicorn, a rainbow unicorn. Well, coming back to reality, in engineering speak, you need a team. Not just any team, but a diverse team. Because it's very hard for anybody really to check 3 of those boxes, right? But you have all these fields to carry. Everybody needs to be good at something. But it's very difficult to hire or optimize for 6 different attributes. So I had a simple rule of thumb. My rule of thumb was I need to find people who are much better than me on at least some of the things. And I just kept going at it, and it worked out okay. So when we first started back in 2017, it was like 4 people. They were all internal. We were all like SRE or SRE adjacent. And we all have this mindset that we need to think about the system property. So we started doing Resolus, which is the performance telemetry work. So that's the one concrete idea we have. Otherwise, we just sort of figuring out. So we did a lot of odd jobs, like talk to different teams and then say, what's bothering you? Like, is there anything else we can do? Someone says, oh, can you install the GPU driver? We're like, okay, maybe, right? And then, sometimes we've run into small opportunities. When I say small opportunity, a couple $1 million here and there. When you have an operational budget of like $300 million a year, you will find $1 million opportunities under the couch. And then we also did lots of favors, right? Not necessarily things that has anything to do with performance engineering. I was at some point in charge of infrastructure GDPR work. I don't even know why, but it's something that nobody wanted to do, and I had the bandwidth to do it, and I did it, and everybody was happy that someone did it, right? So just sort of justifying that you're helpful, valuable, survival mode, I would say. And we made lots of mistakes. Certain things, ideas didn't hold, and we moved on, and we wrote this off, say, don't do this again. So over time, we figured out what is our vision and what is our methodology, and we wrote it down. So once we had a little bit of trust, people saw us as helpful, we actually got enough small wins to start ramping up. And this is where actually a lot of the foundational work started to happen. Right, so with the tracing work, with the long-term metrics work, and all these happened because we ended up hiring people who are extremely, extremely good at those things. So they brought in their vision, and I didn't tell them what to do. I had no idea, but they told me, I'm like, this makes great sense, please, right? And then we dog fooded, and we used our own product, like Resolus, to debug performance incidents. And we were also looking forward. We were looking at all the hardware, things that's crazy hardware things that are happening out there, and then see if any of those would eventually pan out. So speculative, investments. And we went out and continued to talk to everybody. It's like, can we help you now that we have a little bit of tooling and with a bit of insight, we can answer some of those questions. So we did all of those things. And that paid off. So at the beginning of the pandemic, there was a big performance capacity crunch. So at that point, people started noticing us and felt the need to come talk to us. And that's when the consulting models start to flip. Like, instead of going out to reach people, people are coming to us. And then we tried to make them happy, and we tried to make our effort impactful. And as our primary data sets matured, and we started building our own products on top of our platform, people start to use those products, and people start to understand how they can use the same data to do their own thing, when may or may not have to do with performance. And then we got invited to more important projects, mostly to look after the capacity and performance aspect of things, right? People want to tick a box, say, performance-wise, this is fine, and we're often there for it. So all of these made me think, this is really wonderful. People know us. So we turned a lot of effort into intentionally branding ourselves. Like, we are the performance people. We are the systems people. We can help you answer performance adjacent questions, and then really put effort into talks and publishing and even writing papers, stuff like that. So the team got quite big, and then we got all kinds of talent that we didn't used to have. And finally, this would have been would have been a happy ending if we actually executed it, is that once we figure out, we matured, right? So we figured out what are the functionalities that are closely adjacent to performance, which is like things like capacity and a lot of the fleet health stuff. So the idea was not to grow the performance team just linearly, but instead to start having a cluster of teams that work really well together. So the team actually get a little bit smaller because that's easier to work with, but nonetheless, 2022 was everybody was feeling the crunch of the economic downturn. So that's what I'm talking about. When there's a drought, performance team could be the rainmaker because you are the only one who is sitting on top of a bunch of reserve in terms of opportunities, and then you can really make it better for the business, right? So we went with it, and then all of our pent-up projects were green-lighted. It was, for 3 months, it was glorious, and then Elon Musk showed up. So what are the lessons? I would say, especially for a team that really deals with the entire organization, I think the technical and social considerations are equally important. There are several people talking about this, but in my opinion, I have these sort of principles or methodologies for performance engineering. I think they stood the test of time. One is, we need a pipeline, right? There's the opportunity. Some of them may not pan out. Some of them may turn out to be not as useful as they want. So, but if you have a lot of opportunities because we've surveyed the entire system and we measured everything, then eventually you will have a very reliable, consistent pipeline that keep churning out opportunities that you can go after. And for performance teams, usually the best place to look is low-level infrastructure, which affects everybody, or things that takes up like 25, 30, 40% of your entire infrastructure. You know who those are. They're elephants in the room. They're very obvious. And finally, if we want to scale, then it's really about creating platforms and products that allow other people to do similar things. They may not be worth your dedicated team's time, but a local engineer can do that in their spare time, and it turned out to be a very decent win. But I think the other organizational lesson is that design the team to fit the organizational structure. Is it top-down? Is it bottom-up? Do it accordingly. Don't copy what we do if your organization is different, right? And also, outreach is serious work. Treat it as such. Like, adoption is serious work, not just building the product. All of these things, they apply in every sense of that word. And also, people make work happen. I don't need to talk to this room. I'm pretty sure I'm preaching to the choir here, but it's really true. And everybody's strengths and their personality is different, and we have to respect that, right? So I think there's a huge difference between people who are, at the P99 of the talent pool and P50. So when you find such a person, really cherish them because they're very hard to come by. And seek diversity, both in skills and in perspective, because when we do this kind of diverse work, that is really what's needed to deliver. And embrace chance. What I mean by that is, had we found a profiling expert, right, we probably would have built the profiling platform first, and then maybe the metrics platform later. But because of the talent was interested in those things, we let them lead us down the path of least resistance. And it's okay. We can always come back later and make up of the things we didn't build in the first place. Right? So don't have a predetermined mindset, say this has to happen first. As long as everybody is going in the right direction, the particular path is not that important. And finally, it's the things my kids' teacher tell them all the time. Be kind to each other, right? So engineering, software engineering is really a social enterprise, right? To succeed in the long term, we need to be helpful, be generous, make friends, and make it into a culture. Everything will be just so much more enjoyable for everybody. So what happened to IOP after Twitter? So a bunch of my coworkers found really excellent jobs in all kinds of companies. But a number of us banded together and then started doing our own. So what we're doing is not so different from what we used to do at Twitter. But now our goal is different. We want to do something for the industry. We want to build something that everybody can use. So if you want to talk about performance, you know where to find me. I'm local to San Francisco. You might run into me in the street riding my bike. But you can always find me because I'm terminally online. So if you have way too much time on your hands, I have lots of links. You can learn about who we were and what we did. And if you have any questions, please let me know.
So looking back on your journey, sort of meandering through, trying to figure out what was happening, and then when you started to click, what was one of the things that was most surprising on that journey that you never would have expected, but now seems obvious in hindsight?
I think what was a little unexpected might be just how much more valuable understanding the structure of the service and the structure of the distributed system is. Right? Like the index, like, oh, you know, this service talks to that service. Just that fact that there is a connection of any kind exists between those two, or they are two steps away, right? That kind of information, you know, it's not obvious that this is useful for performance, right? It only after several other steps do we get value out of it. But I think if I have to go blindly into a new problem, or maybe seeking a new property that is desirable, I would just say, let's understand the system regardless of the goal. I think now this is sort of becoming actionable to me, but at the time it was somewhat accidental.
You mentioned that you guys are using eBPF for, I guess, per counters for profiling. Like, what kind of metrics, system metrics are you looking for? And then another question I have is, are you like pushing aggregation and like counting in kernel space, like in those eBPF programs, or are you doing that in user space?
Yeah. So eBPF, for those of you who don't know, is sort of like this little bit of a C program you can do that doesn't have loop and has very limited functionality. You can just execute it in kernel, right? It's like God mode, but with limited domain. So the kind of metrics we get from the eBPF, we used to gather things we couldn't get otherwise, right? Like if you want to get the I/O size distribution, like I'm going to the disk or I'm going to the SSD, am I getting 4 bytes or am I getting 16 kilobytes, right? That distribution is quite important because that tells you sort of what is relationship between number of I/O and also the bandwidth they consume. But one thing we realized later on is that even for the things you can get traditionally, like the metrics you have in proxys, right? CPU metrics, sometimes memory metrics. All of these metrics can be obtained by eBPF as well, and actually for far less cost. And there's a reason there's a lot of recent papers at Usenix ATC conference or Usenix OSDI conference, and most of what they did is they do a thing using eBPF in kernel space, and suddenly everything is quantitatively better, right? So we are in this transition of doing as much of the things we want and using eBPF. And we do most of and eBPF is written such that you have this basic data structure in kernel space. You would do your count increments there. But if you want to report anything, usually you have a companion user program to pull the data out and then send it to your stats agent, right? So we do this standard thing where there's a user space and then kernel space sort of duality. And so that's how we do it.
One quick question. Hello, thank you for the presentation. And you mentioned that you can run the scalability values on top of your traces and also analyze dependency graph. And my question is, how do you actually store such data and where?
Sorry, how do I actually
store traces?
Store traces. Okay, so I think we have a real-time data pipeline doing these things. So there's sort of the hidden assumption that things are partitioned by time, right? So traces from today is going to be closer together than traces from yesterday and today. So beyond that, I think there's not an obvious standard for how you would organize them that would answer to every type of query. So we basically didn't bother. We have 5 different indices depending on what level of information you care about. But once you get to the right index, generally what you would do is you actually scan most of them to filter out the ones you want. So it's not the query is not designed to be fast, but it's the best thing to, like, I think the value is that it can answer questions no other data sources can answer, so people put up with the 5-minute delay to execute those queries.
Fantastic. I think that wraps it up. So thank you once again. Yeah, excellent.